Shubhajit, are we expecting more people or shall we start within a minute or two?
Okay, we can start. I should introduce you. So,
We can
good afternoon,
start.
everyone. Today we have our last talk of the day by Aritrabha Majumdar. He has just completed his B.Math here at IISc Bangalore, and he will be talking about random mazes today. Over to you, Aritrabha. The talk.
Okay, thanks a lot, Shubhajit. So today we are going to talk about random mazes, and the maze has a very nice underlying probabilistic structure. So if we want to construct a maze, we at first need something like a base, and then we need paths, blockages, everything. And by the term random maze, what we actually trying to imply is that at every possible time, like suppose at time t is equal to 0, you start exploring the maze. At time is equal to 0, the maze has a fixed structure, and as soon as you enter the maze, some blocks, some paths are introduced with some probabilities, and until unless you explore the entire maze, the maze stays constant. So every time you enter the maze, at every possible time is equal to 0, the maze has a different structure, but it stays same throughout your journey. It is not like that something you have seen in Maze Runner kind of movies, that it is changing structure randomly in between. The structure is fixed at at every moment when you start exploring the maze, and then it stays constant until unless you cross the entire maze. Okay, so there are various ways to describe this type of mazes, but one of the very commonly used way is through the methods of Bernoulli percolation. So how do we define Bernoulli percolation? We usually start with this Z cross Z lattice. So these are basically, these black dots are our lattice points. This is 0, 0, this is 1, 0, and so on and so forth. And if I zoom here a little bit, you can see there are edges in between. So each of these edges are like paths, which are uh, okay, right. Okay. So each of these edges are open with probability p, and they are closed with probability 1 minus p. So let's say you just enter at the origin, then what can be one of the possible configurations of the maze? Let's say this path is open, this path is open, this path is again open, these two paths are open, then this is open, and it then goes on like this. And the paths that I haven't marked with the color red, those are closed paths. So this can be one of the possible structures of the maze. Or let's say we rerun the simulation, or we again try to enter via the origin, then the maze changes its structure, some new edges are introduced, some edges gets removed randomly. So it is not necessary that you will always be able to find an exit. Like if you enter from this part and you want to exit from, let's say, this part, that may not be always possible. For that to happen, the entire maze has to be connected by a contiguous path. And this particular phenomena is known as escaping to infinity. So escaping to infinity is not always possible. So another way we can view escaping at infinity is, let's say we have an infinite water supply here at the origin, and all of these edges are acting like pipelines. Pipelines are open with probability p, and they're closed with probability 1 minus p. So if we have an infinite source of water at the origin, and we want the water to escape like at arbitrary distance from the origin, then we want a continuous channel of pipes which eventually escapes to infinity, a continuous channel of open pipes. So basically in that case, what we need is some sort of like a path like this. So it basically goes on something like this, and this particular continuous path, these are not always present in the lattice for every possible value of P. So again, one can prove via some calculation that there exists a minimum threshold value, which is known as the critical probability. So if P is greater than equal to the critical probability, then such an infinite path will always exist. And if P is less than PC, then with probability 1, we will always find some sort of disassociation between the paths. Like there, like almost surely there will be no infinite cluster like that. And if we talk about percolation in Z only, like the one-dimensional lattice, then it is very easy to see what this critical probability is going to be. So let's say we start at the origin. These are my 1, 2, 3. These are like my nodes. And the distance between them, like the gap between them are the pipelines. So if we want this entire network to be connected starting from the origin, then what do we want? We want all of these pipes to be open. So basically we want this to be open, this to be open, this to be open, and so on and so forth. So we can guarantee that there will obviously exist an infinite cluster if and only if P is equal to PC is equal to 1. Because if PC is less than 1, then we are basically allowing a non-zero probability. Okay, the non-zero probability might be very small, but still it is non-zero. And there exists a non-zero probability that any one of these edges might be closed with that particular value of the probability. Even if it is like say 0.0001, it is still non-zero. Although it is a small value, it is non-zero. So we can see that if we observe every possible pipeline from -1000 to +1000, one or two pipelines may be randomly closed and we won't get an infinite network. So to enforce that we get a infinite network always, for the lattice, not the lattice, sorry, for the one-dimensional percolation, we set the value of critical probability to be 1. And this was fairly obvious that this will be the case during the late 1700s. And after that, people were very confused what the critical probability for this two-dimensional lattice is going to be. And this problem was open until the mid-1980s. And in the mid-1980s, Kirsten proved that the value of PC is exactly going to be 1/2. So if it is like, if the critical probability is even slightly less than 1/2, there is a chance that you will eventually have a cut somewhere in your infinite lattice. But if your value of P is greater than equal to PC, then with probability 1, you will get an unique infinite cluster. But again, so these are some basic ground rules that we are going to set up. I'm not going into the proof and everything because those are a bit complicated and they don't come into the scope of today's discussion. But this particular result that PC is equal to half, this thing was proven by Kirsten in a very long and complicated combinatorial way. But today we are going to discover a very interesting method which gives us this result very easily. And that similar method can be used to compute the value of PC for different kinds of lattices. Like one of the very famous lattice is this honeycomb lattice. And why is this famous? Because this has various physical significance. All of you have seen like plant cells, and most of the plant cells look like this only. So if you want to make a continuous xylem or a continuous phloem network, starting from the very top of the root to the very starting from the very like the bottom part of the root to the top of the tree, in those cases, like if you want to model something like that, a continuous path in the honeycomb lattice basically helps us. So this particular structure has its own physical significance. So that's why this kind of lattice, like honeycomb lattice or triangular lattice, are very well studied in the literature. And like we can use the particular method that we are going to discuss today to compute the critical probability for this kind of lattices. So till now, anyone has any question? Okay, so if you guys have any doubt in between, you can just interrupt me and you can ask the question. It is not like that you have to wait until I finish talking. So you can just interrupt me in the middle of the talk and you can ask. Okay, so we have tried to build an intuition like how the thing will look like, but let's give a formal definition. And if you want to define it formally, it is basically like a graph with the vertex set to be all the lattice points present, and we have edges between them, and each edge is open with probability p and closed with probability 1 minus p, and we assign that openness or closeness by the value 1 and 0. Like w is a configuration of all the available edges, and in a particular configuration an edge is open if omega of that edge is 1, and it is closed if omega of that edge is 0. So basically what I'm trying to say is probability that omega of E is 1, that is given by P, and the probability that omega of E is 0, that is given by 1 minus P. So for those who know a little bit of probability, so what is the definition of the critical probability? Or it is an undefined term in the literature concerned? No, it is not an undefined term in the literature concerned. So you can define critical probability in two ways. Okay, so if you want to define critical probability, one thing that we are concerned about is the mean cluster size. So, okay, again, what is cluster? Cluster is nothing but a contiguous network of open paths. And the mean cluster size is often defined as chi of p. So, of course, it will be a function of p. Like if p is equal to 1, your entire network is going to be an open cluster. So the mean size of the open cluster is a function of p. And if we want to define critical probability, probability is defined like the infimum of all those values for which the size of chi p is infinite. So that is how we define critical probability. Okay. And yeah, so I was in the okay, so I was discussing this particular definition, and those of you who know a little bit of probability, you guys can relate that this is basically the definition of a Bernoulli random variable. So that's why this particular percolation model is known as two-dimensional Bernoulli percolation. Okay, so now we will move on to the next slide. And okay, so now we have open paths and boundary crossings. So we define omega to be the union of all open edges as a subset of R2. So basically, now what we are going to do, we will embed our entire Z2 over R2, and then we will look into the paths and study them. So this particular term is not really necessary because eventually we will eventually bring every continuous cases down to discrete case and we will study them. So this is basically like to build a rigorous mathematical framework in order to study things. But for our intuition, these things are not really necessary. And now we want to define boundary and stuff. So let's say I have some sort of percolation network like this. So this is, I'm drawing a subset of Z2. And after that, I consider a particular subset like this. Okay. So this is let's say a particular subset. So this is a closed and bounded subset because, okay, this is of course bounded because we can see 4 clear boundaries, and it is also closed. So this is the D in this case, and these 4 sides are the boundaries of D, which is defined by del of D. And the boundary crossing is basically a path which starts at any one of the boundaries, ends at any another boundary, and consists of all the open paths. So that is how a boundary crossing is defined. And it can be left to bottom crossing, left to right crossing, top to bottom crossing, anything. But today we are mostly concerned about left to right crossings. Okay, so my bad. So left to right crossing. We're only concerned about them. So yeah, so crossing is basically nothing but union of open paths that relate to particular points onto particular boundaries. And after that, we have the event of rectangle crossing probability. So we define a new event CMN, which is basically the event that the rectangle 0, m cross 0, n is crossed from the left side to the right side. So how does the structure look like? Okay, so observe one thing, that now we are defining the rectangle as the product of the Cartesian product of two closed intervals. And we can do that because we initially embedded the Z2 in R2 and we started studying it. Otherwise, there is no real meaning of defining closed set in Z2 like this. Okay, so what we basically have, okay, so the event, let me write, yeah, so the event C of m comma n basically means we have a rectangle which has m lattice points in the length part and n lattice points in the width part, and we have a continuous path like open union of open paths like this, which connects the left side to the right side. This is known as C. This event is basically described as CMN. And the probability of CMN is known as the crossing probability. And now we have to interesting monotonicity property, that is probability of CMN. This thing is non-decreasing in n and non-increasing in m. Can you guys see why this should happen? Anyone has any idea, any clue?
What does non-decreasing in n means?
Okay, so non-decreasing in n means, so let's say you are increasing the width of the rectangle. So at first, let's say it was m cross 1, the value of n was 1. Now you have m cross 2. So what I'm trying to say is probability of C of m n1 should be greater than equal to probability of C m comma n2 if n1 is greater than equal to n2. Always. This is the meaning of non-decreasing probability. So like as n increases, the probability will be greater than or equal to.
Got it.
Okay. Okay, so it is basically non-decreasing because we are interested in only a left to right crossing. We are not interested in a top to bottom crossing. So it really doesn't matter if the height increases. This, see, like if we can find a valid available open path in a m cross n rectangle, now let's say we increase the length by t units for the new rectangle. We just increase the width by t units like this. So this is t unit. But in this new rectangle, which is m cross n plus t, this red path is still a left to right crossing. So it is not like that if we increase the length, the probability of having a left to right crossing will eventually decrease. It is at least equal, or another thing that can happen, that we can have another open path like this. So the probability is non-decreasing. But what happens if we increase the length m? If we increase the length m, in that case, let's say this was my initial configuration. This is the length m, this is the width n, and the thing goes on like this. Now my plan is to increase the length. So let's say I increase the length a little bit. Let's say again my bad. Let's say I again increase it by some 2 units, let's say. So this is 2 unit, this is again n. So now what I want to have is, now if I want to have a left to right crossing, I should have a path from this boundary to this boundary also. And it is not always guaranteed that I will find an open path from this boundary to this boundary. If I have, then it is well and good. But it is not always necessary, right, that I have an open path from this boundary to this boundary. Okay, so what Shreya is saying, like every path also crosses a narrower rectangle, but not every path that crosses a narrow rectangle may cross a wider one. Exactly. Exactly the same thing. So it is basically like what Shreya has said. So basically, if we keep the height constant, and okay, so I'm mentioning this to be the width and this to be the height. If we keep the width constant and we just increase the height, the width stays the same, and that is the only thing matter for the left to right crossing. So that's why the probability is non-decreasing. But if we eventually increase the width, keeping the height constant, so in that case, we may encounter some region where we don't have a left to right crossing. So that's why probability of C. Okay, so for but each case m comma n, we have more than one way to continue our graph as well. Abhinav, can you please like unmute yourself and explain?
So like in that n comma m plus 2 rectangle, the same graph we can continue it in many ways. We can join that the point that at which the graph
See,
plane
we
gets.
can, yeah, of course, we can continue it in many ways, but
So,
in order to continue, we need to have open paths, right? There is no guarantee that in this region, any path will be open. In a particular configuration, it is not really necessary that you are going to have open path like this. So,
right.
so basically what I'm trying to say is, uh, let's say you have some critical probability, okay, some value of P, which is less than the critical probability. Okay. And you are present on a particular percolation model like this, and you have an open cluster. Let's say the open cluster looks something like this. Okay, let's say the open cluster looks something like this. So inside this open cluster, every blue edge is open. Okay, now if now you are trying to expand the size of the cluster, so what do you want to see? You want to see the behavior of the model or anything for a bigger cluster. So you are extending the height, width, and everything. But now, like, what I'm trying to say is, it might be possible that the other edges present here, like say this edge, this edge, this edge, all of these edges are closed. So in practice, you might study I mean, you obviously you can study a bigger network, but that really doesn't help you, because inside that bigger network, every other edge is basically closed. They are not open in that particular configuration. So that's what I'm trying to say, that in, like, initially when the rectangle was m cross n, we had an open path like this. But whenever I'm increasing it, whenever I'm increasing the width by some particular unit, we don't really know that whether in this rectangle, like in this n cross 2 rectangle, we will have a continuous stretch of open paths from this red boundary to this red boundary.
So this would have its own configurations, right?
Yeah, no, 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 no. This won't have its own configuration. Remember, like I mentioned, that whenever we enter 0, comma 0, we fix a snapshot of the configuration. So the entire configuration is fixed now for the entire lattice Z2, and we are trying to, like, we had this initial network, and now we are just trying to expand it. Like,
Okay, got it.
okay. So basically what happens in this case is, like, if we want to ensure that there will be a crossing from, let's say this is my m plus 2 now, and this is n. If I want to ensure that this is going to happen, this is basically what? For this, I have to ensure that this occurs from m to n. This occurs. This we know that this will occur. Along with that, we need another intersection, and that intersection is from this boundary to this boundary. We also need to have this path. And what I'm trying to say is, this second event is not really guaranteed. Okay,
So this will be less than or equal to the previous.
exactly. And see, again, you can see that having a path from, let's say this point is A, this point is B, and here I mark another point C. Having a path from A to B is completely independent of the fact that we have a path from B to C or not. So basically having these two disjoint paths are kind of like independent events. So like if you try to add the probability of this will basically become the product. And as this is not really guaranteed, so if it is 0, then we are done. It is strictly less. And even if it happens, like it is just exactly equal to or less than equal to. So that's why the event is non-increasing.
Yeah, got it, sir.
Oh, okay. So that is how we define the crossing probability. And after that, I have, yeah, two very easy example. One is, let's say the height is 0. So the height is 0 means I'm basically considering this in the normal linear, I mean this line of integers, I'm considering the percolation. So I am saying that there will be a rectangular crossing from the origin to the point M. Okay, I think I should change my color. Okay, so starting from the origin, we will have a crossing at the point M. So if I want to have a crossing in this case, what do I need to have? I need all of these intermediate paths to be open. So I have altogether m many intermediate paths. And if I keep my value of p to be half, like, okay, so now I am considering a Bernoulli percolation with the value of the parameter to be half. So it is basically like a tossing of a fair coin. If the fair coin lands a head, the path is open, and if it lands a tail, the path is closed. So if we consider it like that, so each of the path, like each of these orange paths have a probability of being open. I mean, the probability of being open is half exactly. And we have m many of them, all of them are independent. So the probability of everything being open is 1 by 2 to the power m. So that's why it is the horizontal crossing probability. And now if I consider this particular example where we have a column-like structure, a column of length n, and the width is only 1, in that case, if I want to have a left to right crossing again, then I mean, how can we calculate that? So let's at first embed this particular structure into a lattice. So if we embed this into the lattice, okay, where is my lattice? That was in the very first page. Okay, wait, let me go there. Yeah. So let's say we're embedding this particular fine structure into the lattice. So as of now, let's assume the value of n is 4. So what do we have? We have 1, 2, 3, 4. And the width was only 1. Okay. So if we are willing to have a left to right crossing, either we want this path to be open, or we want this path to be open, or we want this path to be open, or this to be open, or this to be open. If any one of them is open, we will have a left to right crossing. So how can we how can we calculate this probability? So basically this is probability of any one is open, and that is basically equal to 1 minus the probability of all of them are closed, all of them closed. And here we have say see, we had n equal to 4, and that's why we are having 5 many paths or edges. So for n, you can prove that this will be basically n plus 1. So half to the power n plus 1. That is the probability of having a left to right connection in this particular lattice, 1 comma n. And after that, I have a small exercise for you guys that you can try in your home. And yeah, of course, that exercise is a little bit tricky. For any lattice with length m and width 1, you can find the crossing probability like this. Okay, so if you guys are if you guys have seen this kind of structures before, you will obviously realize that okay, there is some sort of recurrence relation involved here, and I am going to write the recurrence relation explicitly for your help. So the recurrence relation will look something like this. it is P sub m plus 2, that is equal to 3/4 of P sub m plus 1 minus 1 by 16th of P sub m. So if you try to compute this recurrence relation, you will eventually find this out. And how to compute this? In order to compute this thing, what you basically can do is like take a m cross n rectangle, just try to just consider this extension of length 1. And if we have an open path from this point to this point, like as the height of the rectangle is only 1, the path will look like this only. So it will start from either here, it will go here, or it will start from here and it will go here, something like that. And now what can happen? Either this, the joining of these two will be open, like the joining of these two particular node will be open, or if it is connected like this, the joining of these two particular node will be open, or both of them can be open. So you just try to compute with a little bit of inclusion exclusion and you will eventually get this particular recurrence relation. Okay. And now we can move on to the next topic, and that is the symmetry of critical Bernoulli percolations. Okay, so this is not really anything very interesting. And okay, so here things are written in a bit rigorous way, like if sigma is a symmetric group generated by lattice translation, these and that. Okay, so these are very, very fancy language. We don't really have to care about any of these. What basically I'm trying to say is, let's say you have a network like this. Let's say this is M, this is N. You have some sort of network like this. And now what you do, you translate the origin. So basically you pick up a particular vertex x comma y and you send it to some, say, x comma a comma y plus b, x plus a comma y plus b. So basically the entire lattice stays the same. It just basically gets translated. And the new lattice looks something like this. The length is still m cross n, just all the value of the coordinates change. And the path also looks the same. So what does our intuition say us? Like the probability for crossing this particular lattice, let's say L1 or this particular configuration, and let's call this L2. Probability that we have a crossing in L1 should be equal to the probability of crossing in L2. And similarly, if we just rotate this lattice, let's say we rotate it by 90 degree, rotate by 90 degree, then what can we have? Then we have a configuration like this. This is N, this is M, and we have a top to bottom crossing. We say this probability is exactly equal to the probability of a horizontal crossing like this. We have the same path. So now you can basically compose these things, and like by that you can also claim that, okay, probability of this being M, this being N. Okay, so the path here looks a little bit like this. So we will make it like this. The probability of this path is just equal to the probability of this path. So basically, if you rotate by 180 degrees also, it doesn't matter. So this is basically the invariance of symmetries of Z2. And again, there are some brutal, crude ways to prove these things very rigorously. But as of now, the intuition is enough. And then we have increasing event and the idea of Harris-FKT inequality. So increasing event basically means that, let's say you have two particular configurations. One is the configuration W1 and another one is the configuration W2. Okay. And we pick up a particular event E, let's say, and we say this event E is increasing if this happens, like W1 belongs to E, W1 is always less than equal to W2, and that implies W2 belongs to E. Okay, now what this W2 less than equal to W1 thing means? This means that, like, you pick any edge. Okay, I think I should change the color. Okay, if you pick any edge, E is any edge from the event E, then W1 of E, see, W1 or W2 of E is either 0 or 1. So it is basically like a binary variable kind of thing. So W1 of E should always be less than equal to W2 of E. That is the meaning of an increasing configuration. And how you can have an increasing configuration? By, let's say, considering a more connected kind of structure. So, okay, so generating something like that is a bit of a pain, but yeah, this is the intuition. So this we call to be an increasing event. And after that, we say that if we have two increasing events like this, E1 and E2, then this particular inequality is satisfied. Okay. If you want to prove this, you can prove a simpler version, which basically says that covariance of indicator of event E1 and indicator of event E2, this thing is always greater than equal to 0. I'm not going to formally define what covariance is and everything. If you guys are interested and you know, you can prove this thing. And another interesting remark that I would like to make, that this particular inequality was given by Harris in the beginning of 1900s. And after that, three scientists, I don't remember their full name, but their initial is FKG. They've proven this for an even general setup. For those people who know a little bit of measure theory, for them, I would like to say this particular part. And that is, let's say you have a measurable space A along with some particular measure mu. And in that particular case, if f and g are measurable functions, then FKG inequality says that expectation of fg is greater than equal to expectation of f times expectation of g. So these two things look very similar. Of course, they are similar because in this particular case, what we have is the mu is nothing but our probability measure, and the function f and g are nothing but our indicator functions, because indicator of expectation of the indicator is nothing but the probability. Okay, so that's why this inequality is more famously known as Harris FKG inequality. And then we have a concept of planar duality. So planar duality is nothing but we take a graph and we try to construct its dual. Okay, so why should two increasing events should be positively correlated just because edges are independent? Uh, okay, okay, that's a really nice question, but today I think I'm a little bit short of time to prove that, because it is actually a very long and involving proof. I mean, it is actually a little bit easy to prove for symmetric Bernoulli percolation, specifically when p is equal to half. But even if you want to prove it for any general configuration, things are a little bit trickier. And if you want to prove it for the most general case, then it is a very long and involving calculation. So I think today I'm going to skip that particular thing. Okay, now over to the construction of the dual graph. Okay, so the dual graph has vertices half comma half plus z2. So it is basically nothing but we are kind of origin shifting or translating the entire set of edges we had. And W star of E star. Okay, so W star is basically the corresponding dual configuration we had for W or omega. And E star is the corresponding dual H. And that is basically 1 minus W of E. So for each open edge, in omega, we have a closed edge in omega star. And that is what we are trying to observe. Okay, so let's see an example. I think that in that case it will be clear. So this is our primal configuration, and this blue path is basically a left to right crossing. So now if we want to do if we want to draw a dual configuration of this thing, how the dual configuration would look like? The dual configuration looks like this. Okay. I am choosing black ink to draw the dual edges. Okay, so this was an original open path in my graph. So the corresponding dual edge will be this edge, like that particular edge in the dual graph that crosses the open edge of the primal graph, and this particular black edge is closed. Similarly, this particular edge is also closed. This 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 is also closed. And this is also closed. So all of the edges marked by black are closed edges. So basically, W star of E star in all these cases is 0, which is basically 1 minus 1. And this particular value of 1 minus 1 is basically 1 minus W of E. And all of these ones corresponds to this particular blue colored edges like this. So that is how we draw dual configuration. Okay. So now once we have got into the dual configuration, let's spice things up a little bit. Now we go for dual crossing or block primary crossings. And here we have a very interesting result that is known as the square estimate, that for every integer n greater than or equal to 1, this particular inequality is satisfied. So basically you have let's say this is n plus 1 and this is n. The probability that you will have a horizontal crossing like this is exactly equal to half. Okay, half is a very good value of probability, and yeah, this is actually a little bit awe-inspiring result, but it is actually not that hard to notice once you observe a couple of things. At first, let us talk about symmetries. Okay, by the symmetry property, what do we know? That these two things are equal. This particular horizontal crossing probability is equal to this particular vertical crossing probability. This is n plus 1. So it is basically what we are doing. We are just rotating the entire configuration by 90 degrees. And we have just seen that these probabilities are invariant under rotation and translation. So these two probabilities are equal, exactly equal. And now we're going to have a very interesting realization. What is that realization? Let's say we have a closed subset like this. Let's say this is any arbitrary length n and this is n. And we have a horizontal crossing like this. This implies we cannot have a vertical crossing in the dual configuration. Why is that? Because if we want a vertical crossing in the dual configuration, then what do we need? We need a continuous collection of open edges, right? So let's say I have a continuous collection of open edges for the sake of contradiction, and the open edges look something like this. Okay, so the open edge of the dual graph and the open edge of the primal graph intersect at some point. Okay, now let's zoom into this particular area. In this particular area, what are we having? We have something like a series of open paths like this in the primal graph and a series of open paths like this in the dual graph. But is that ever possible? No, because whenever a dual edge crosses a primal edge and the primal edge is open, the dual edge has to be closed. So that's why these two events can't happen simultaneously. You guys have any doubt understanding this particular part? Hello?
No.
Okay. So this is basically the key point that we have to observe, that if we have a horizontal crossing, then the dual graph can't have a vertical crossing, because in order to have a vertical crossing, we need a continuous union of open paths, and some edge of that open path will eventually intersect the horizontal crossing, and that is never possible. Like the dual open dual edge and the open primal edge can never cross like that. So what do we have? Now just replace m by n plus 1. And what are we getting? We are getting that this particular event, that you have n plus 1 here and n here, this is basically nothing but the complement of this event. This is n plus 1. We have a top to bottom crossing. This is basically the complement of this event, because two of them can never happen together. And yeah, if you do a little bit of counting, you can see that, like, if the primal graph has length n and width n plus 1, the dual graph will basically like have opposite attributes. The length will be n plus 1 and the width will become n. You can show that. And from this particular relation and the symmetry above, what do we have? Okay, so as these events are kind of complement of each other, we have that this plus probability of this vertical crossing, this is basically 1, and these two are equal, so 2 times the probability of this single horizontal crossing, 2 times the probability of this single horizontal crossing is 1. So the probability of horizontal crossing is exactly 1 by 2. Okay. So this is a very interesting result, which will eventually help us to prove that we can always cross a random maze, no matter how big the size is. Okay, so I will skip this part for now. Like if I get adequate time, I will come to this later. Okay, now we define rectangle crossing property. What is a rectangle crossing property? Let's say we have a rectangle of length n and width lambda n. So this lambda is basically known as the aspect ratio. I think all of you are familiar with the concept of aspect ratio. Like you guys have seen it in your monitor TV, like 16:9, 3:4, 3:2, all of these things. So this lambda is basically an aspect ratio. So the rectangle crossing property holds for every lambda greater than equal to 0 if this particular relation is satisfied. That infimum of the probability that a horizontal crossing for this rectangle exists, the infimum over all n is more than 0. In that case, we say that a crossing property exists. So it is basically like that you fix a particular lambda and do some simulation, find the value of this particular event for all the n's, and just try to find the smallest value. If the smallest probability is non-zero, then basically the random maze is crossable. So okay, so I will try to formalize this idea a bit more. Basically what it is trying to say is, if you can cross a smaller maze, let's say you have a random maze like this, if you can cross a smaller maze and then I just increase the size of the maze eventually, you will be able to cross that. You will of course be able to cross that with a higher probability. This might sound a little bit counterintuitive, but once we go through the proof, we can see that okay, it is actually not that counterintuitive, to be honest. Okay. So now we can see that the crossing property holds for every lambda less than equal to 1. Okay, why does it hold for every lambda less than equal to 1? If lambda is equal to 1, what do we have? We have probability of Cn comma n that is more than 0. Now what do we know? We know that probability of C n plus 1 comma n is exactly equal to half, which is more than 0. And now what do we know? That this particular function, probability of C m comma n, this thing is non-increasing in m. Okay. So basically probability of C n comma n, this thing is greater than equal to this. So probability of Cn comma n is obviously more than 0. For lambda equal to 1, this thing holds. And even for lambda less than 1, by similar logic, we can prove this thing. So the only difficult case, which is now remain to prove, is what happens when lambda is more than 1. Okay. So even for lambda being more than 1, it is not that tough to prove. Again, why? No, okay. So yeah, for lambda more than 1, it is a bit tough to prove. But here our strategy will be we will be proving it for a particular value of lambda, and then we will draw some conclusion. Okay. So now here comes the interesting result for lambda and mu. Okay, so these are two different aspect ratios, lambda and mu. And if both of them are more than 1, then we have this particular relation between them. So what is it basically saying? See, mu is a smaller aspect ratio than lambda. And if you can cross it for, let's say, this is your rectangle with aspect ratio mu, and you are crossing this. And if this thing is strictly more than 0, you are just taking more than one power, like you are taking a positive power of this thing. So if you are taking a positive power of this thing, the probability basically increases. So if you are able to cross a smaller maze, you can obviously be able to cross a bigger maze. So, and now if you want to prove this thing, the proof is a little bit involved. So I will just do the proof sketch. If you are interested, you can complete the proof by yourself. So via induction, what we are trying to prove is C of n plus ik comma n. This thing is greater than equal to the C of n plus k comma n whole to the power I times probability of C of n comma n whole to the power I minus 1. Okay, how to prove this? You can prove this via induction. Like you can see this is, you can prove that this is very trivial for I equal to 1. So trivial for I is equal to 1. And then what one can do? You can like fix I to be some t. And now for I is equal to t plus 1, you can do this thing. So for I is equal to t plus 1, what you can do is you will take a big rectangle and the width will be n plus t plus 1 times k. And so this is the width and the length is n. We will divide it into some subparts. So what are the subparts? The subparts are, let's say this part is n plus k, and this entire part over here is n plus tk. And yeah.
Sir, only TK, right?
Sorry.
Sir, N we have used.
Sorry. Can you please repeat it once again?
Sir, N plus K, and then that should be TK, right? Just TK.
Yeah. Sorry. Yeah. My bad. This should be TK. Yeah. This is only TK. Yes. Thank you for pointing out. Okay. Okay. So after this, what can we do? Okay, and we will consider another intermediate rectangle and another intermediate square, which is of size n. So this is basically an n cross n square. Now we want to have a contiguous path from left to right. Okay. So by our induction statement, what do we know? By our induction statement, we know that such a path exists from here to here, and such a path exists from here to here. Okay. So now if we want to have a contiguous path, what can we do? Again, we can use the same logic we used during the duals, during constructing the duals, that if we have a vertical path like this, the vertical path will eventually cross the two horizontal paths, and then we can have a contiguous path like this. Because see, of course, we can have configurations like this, and just gluing two rectangles doesn't really give us a continuous path from this edge to this edge. So in order to like secure the existence of a continuous path, we have to introduce the idea of a vertical crossing as well. So the probability that we have a horizontal crossing in the bigger rectangle, that is basically less than equal to the probability that my bad, I have reversed the sign. That is greater than equal to the probability that a orange crossing exists. My bad. The probability that an orange crossing exists times again another probability that such an orange crossing exists, because existence of these orange and blue crossings are independent of each other. So that's why the probabilities are basically getting multiplied. So we had intersection while writing the events. Now we are just basically multiplying them times the probability that a vertical crossing will exist. And after that, if you do the computation, you can prove this particular result mentioned here. And then what you can do, you will just fix some value of parameters. Like you can fix k to be floor of mu n minus n, and I to be floor means ceiling of mu n minus n, and I is ceiling of lambda minus 1 by mu minus 1. Okay. So this particular result can be proved in various other ways, but this particular proof is a little bit interesting for us because this was given by Paul Ardosh. And that's why you can see that this proof is a little bit more pictorial, a little bit combi involved, and has this kind of weird manipulations. Okay, so now once we have proved this particular result, we are basically like kind of done about what we are trying to say. As lambda is a bigger aspect ratio than mu, and if probability of C of mu n comma n is more than 0, then we have probability of C lambda n comma n. This has to be bigger than 0. So let's say you have a rectangle like this. So this is basically mu n cross n, and then you are just increasing the aspect ratio like this. So you are making this bigger. So what they're trying to say is, okay, so if you have an open path in the maze from this end to this end, you can obviously find an open path which starts from this end and it eventually traces back to some point of this end. And this is basically like kind of guaranteed. You will always find such a path like this. So that's why we sometimes say that, okay, if you have a random maze and you can solve the random maze at a smaller aspect ratio or at a smaller scale, you can scale it arbitrarily big as you want, you will obviously find a solution. There exists some solution for that bigger maze also. And this particular result has some very interesting application while studying some geological properties of some rocks, this and that. And these also have some very interesting application in computer vision. So some of you must have heard of this game that you have such rectangular grids like this, and each of the grid basically survives or dies out. And eventually, like, you have a grid structure like this, so like these four corner grids are survived, this intermediate grid will also survive. And then you run this simulation for a long time, it generates some particular patterns. This is still an open problem, that why we have some particular patterns like this, but some part of this particular, like some justification that why this particular patterns can be formed have been given by this particular theory. Like basically there they have taken each of these uh, boxes to be an edge, like the edges either are open or closed, so they basically survive or die. And after that they impose some initial, some additional condition to make the models kind of equivalent, and after that, using this particular result, they can predict something about the upcoming pattern. But this is still a work in development, and this is being done by Hugo Dominil Kopin. Some of you might have heard his name. He's a Nobel Prize receiver. And yeah, this work is currently being done jointly by Hugo Dominil Kopin and Tom Hutchcroft. They're trying to study the problem from a completely different point of view, and let us see whether they become successful or not. Okay. And then we have a couple of lemmas, but again, these are not that important. I will eventually send the notes, and like Shubhajit will share those notes to you guys. You guys can have a look if you want. But the last thing that we want to prove is this particular result. And again, I won't give a proof, I will just give an outline, which is known as the RSW theory, or Russo Seymour Welsh theory, which says that for every lambda greater than or equal to 0, the square is crossable. So basically, take any lambda you want, this thing is always satisfied. And how does it make sense? See, for lambda less than or equal to 1, we have already proven this. So we only need to prove this for lambda more than 1. And if we can show that there exists a lambda more than 1 such that horizontal crossing exists, then by the proposition that we have just proven, which involved lambda and mu, from that we can conclude that you take any arbitrary large lambda, so in any arbitrary large, let's say lambda star, which is more than lambda, for that also an horizontal crossing will eventually exist. So what we try to do, this thing was proven by Russo, and this particular result was proven by Seymour and Welsh, that if you take lambda to be 3/2, these are two interesting lower bounds of the probability. This lower bound is actually a little bit easy to prove. And how can someone prove that? In order to prove that, we basically involve an idea of like crossing the rectangle with the lowest possible path. So what is the lowest possible path? The lowest possible path basically means that, see, each of these paths divides your entire rectangular grid into two areas. So we basically say that the lowest possible path is such a path that the area bounded below has to be the smallest among all of them. And if you want, you can prove that such a path is always unique due to Jordan curve theorem. And so basically we take a lowest most path like this, and then we try to partition this path, and we give a upper probability bound, and by this things can be shown. So I don't know whether I have time to do it or not. Okay, so I have only 5 minutes left, so I won't be able to do the proof. But yeah, so if you guys want, I can share the proof later, or like it is also mentioned in the references that I have given. But it is a really interesting proof. So this particular exploration proof, which is a very symmetry and combinatorics involving proof, that shows that the lower value of the probability is 2 to the power minus 16. But the proof given by Seymour and Welsh, this involves a very interesting method which is known as renormalization procedures. Like if some of you are interested in physics, this will be like one of the very common term that you will use very often, renormalization. So this particular proof done by renormalization technique, this particular proof technique is used in various fields of statistical physics nowadays. So although these proofs give us a very arbitrary bound, like this 51891, this particular number has no such physical significance. This 2 to the power minus 16 is very much significant once you start doing the proof. But this particular number, to be honest, doesn't really have any physical significance. But the proof technique developed by them is like of great use. So that's why we still regard this proof to be a very good proof. And after that, we have some interesting corollary. And what is that corollary? The corollary says that if there is a constant C loop more than 0, such that the probability of this particular event is more than C loop. And what is that event? That event is basically, let's say you have a rectangle like this. This is 3n, this is n. And you have a square in between. So we will have a loop which basically avoids a square. So the probability that we will have a loop like this is always non-zero. And we can find a C loop, a value of this particular constant in such case always. And another interesting result is known as the one-arm probability. And this result says that, let's say you have a percolation lattice like this, and this is your origin. This is your origin. So you start running from the origin, and the probability that origin is connected to some boundary of this n cross n rectangle, this is bounded above by c to the power n minus alpha, and there is another constant by which it is bounded below. So like the existence of a path is not really non-zero. You can prove it via this. And this particular result says that, okay, although it is non-zero, it decreases exponentially as n grows. So the probability eventually becomes very, very small, even if n increases slightly. So these are two interesting results, and these two results together combined can prove Kirsten's theorem very easily. Like it is a 3 or 4 liner proof. Okay. So after that, this is kind of like a mind map. If you guys want to explore this topic a little more. And okay, so just to sum it up, what have we done today? Today we have done Bernoulli percolation, and from that we have derived the idea of a random maze. And from random maze we have seen horizontal crossing and also vertical crossing in the dual graph G star. And from that, we have eventually proven Russo Seymour Welsh theorem, which says that if you can cross Bangalore traffic, you can travel the entire India. And again, this particular idea of random maze and RSW is also very much involving in game designs, because some of the games use some random mechanics to like make your user experience better, so that you don't really have to solve the same maze or same puzzles over and over again. In that cases, they use the same kind of idea that, okay, we start with a very basic model of the puzzle or maze that is solvable. Now we start building upon that, keeping the configuration same. Even if you make the maze bigger or the puzzle even harder, that is not really unsolvable because of this particular result. And after that, this result, okay, so I mentioned that I will eventually go back to the particular slide that I have missed earlier, which is Yeah, Cardy's formula. Okay, so there are many of you guys who don't really like probability, or you guys haven't explored probability that much. This slide is for you guys. So this particular constant, or rather function f lambda, so Cardy like made a conjecture about this, and he said that this looks something like uh, gamma of 3 by 2 gamma half divided by gamma of 1 by 4 times 2f1 half 1/4 3 by 2 lambda. So what is this 2f1 function? This function is known as, this is a very interesting function if you study analysis, specifically complex analysis. This is known as Gaussian hypergeometric function. And let's say you have a particular polynomial like this. Let's say fx is equal to a naught plus a1x going until an x power n. This is your polynomial, and these all of these coefficients are basically random variables under some distribution, and you are trying to find the roots or the location of the roots, whether this function is integrable, differentiable, maxima, minima, everything. These random phenomena are often governed by this particular result in RSW theory, and this can be even boiled down to a much more general configuration. Like if you have an arbitrary set like this and you pick four random points over here, like let's say A, B, and C, D, and then you have two arcs like this. Let's say this arc is A, B, and this arc is C, D. The probability that you will have a horizontal crossing from this AB arc to CD arc, that is basically equal to this particular probability. So here we define aspect ratio in a bit different way, but again, all of these different results in complex analysis, in probability, in percolation, these things are very highly correlated. Yeah, so now I think it is a good time to stop. You guys have any doubts in any particular part? Okay, at P is equal to PC, does PCMN converge to a non-trivial? Oh, okay. Just give me a second. At P is equal to PC, that does PCMN converge to a non-trivial limit as Mn approaches to infinity? Yes, it converges. Of course, it converges. And okay, see, let's say you have something like this. Mn, M and N both are tending to infinity. So what are you basically having? You are having an infinite lattice, right? You are having an infinite lattice, and let's say this is not origin. It is some random, the starting point is some random a comma b. But again, I have said that this horizontal crossing probability, this is invariant under translation and rotation. So you just make it like you just translate it back to the origin. And basically what you are trying to compute, you are trying to compute that you have some point at the y-axis, and from the y-axis you can have an infinite horizontal network like this. Then what can you do? You just take this part and rotate it in such a way such that this entire path is rotated something like this, and it looks like this. So it starts at this very point and it eventually looks like this. So basically the event that you have mentioned is basically equal to the probability of the event that we have an infinite cluster. And at P is equal, and for all P greater than equal to PC, that probability is basically 1. So again, here I have mentioned a term which is known as conformal invariance. This conformal invariance is a very interesting key feature of this percolation networks. So conformal invariance basically means the probability is invariant under scaling, invariant under translation, and invariant under rotations as well. That particular property ensures that the event that Shreya has mentioned in the chat, that C sub m comma n as mn intends to infinity, that is basically like having a horizontal crossing from the y-axis to the infinity. Now we do some translation, rotation, and scaling. That is basically like we have an infinite path which starts at the origin and goes to infinity. Okay, so anyone has any other question? Sorry for the background noise, but if anyone has any doubt, they can write in the chat, or they can just like open up the mic and they can speak. And I'm very sorry if some of you didn't understand what the hell is going on in this entire talk. I'm very sorry for that. I think I was a little bit sloppy. But again, if you have any doubt, you can just text me or email me also, asking the doubts anytime. Okay. So, okay. So is asking, sir, what's the condition for existence of horizontal and vertical crossing in dual configuration? Okay. So let's say you have a horizontal crossing in the dual configuration. So this is your dual graph. You have a horizontal crossing like this. Okay. So in dual, you have horizontal crossing means in your original or primal configuration, you can't really have a vertical crossing. So your primal configuration will look like this. Oh, again, I have made it bad. Okay, so your primal configuration would look something like this. There you can't really have a vertical crossing. Vertical not allowed. Why? Again, because if you have a horizontal crossing in the dual configuration and vertical crossing in the primal configuration, you have an intersection. And in the point of intersection, what can we see? We have a horizontal sequence of open paths and a vertical sequence of open dual paths intersecting at some point, and the intersection can't happen because for every open primal path, we have a closed dual path. But here for this open primal path, we are having an open dual path, which is a contradiction. So if you have a vertical crossing in your dual configuration, sorry, if you have a horizontal crossing in your dual configuration, you can't have a vertical crossing in your original configuration. And if you have a horizontal crossing in your dual configuration, and if you have a vertical crossing in your dual configuration, you can't have a horizontal crossing in your dual configuration. So if we just try to understand the relation between primal and dual, we can't say what do we need. I mean, we can specify what can't happen. Like I think you are getting my point. Like if we have a horizontal crossing, we can't have a vertical crossing. But we can't really say that, okay, we need these, and these things. Then we can ensure there will be a horizontal crossing in the dual graph. We can list what we don't want. We don't know what we want. I think it's clear. Anyone has any other question? Snigdha, Obrodeep, Avinav, Nishchay, Ritvik. Anyone, any question? Okay. Shubhajit, are you there?
Yes, Aritrabha.
Okay, so I think I would like to conclude the talk now, and uh, I will just share the materials to you. You can just post them over. So I will be basically sending the slide and the reference material, right? I think that would be enough.
Yes.
Oh, okay. Sure. Okay, guys, thank you very much. And again, if you have any doubt, Abhinav, you were saying something?
Yes,
Okay.
thanks a lot for this class.
Uh, okay, thank you. And again, if you guys have any doubt, any question regarding any part, any minute detail, even it can be the most trivial thing, but again, if you have any doubt, feel free to ask me. Like you can mail me, you can text me, whatever. Okay, so I'm concluding the meeting and thank you. Thank you very much.